Before we go to the lecture, let's address a couple questions people asked from the previous lecture. I remember Zedong, you asked why not just put this perturbed KKT condition as t equals to infinity, right, from the previous lecture. And there are a couple other questions, things like what are the convergence criteria for Newton's method in solving nonlinear equations? So thank you guys for asking those questions. You also helped me improve my understanding of how those algorithms work. First of all, about the Newton's method in solving nonlinear equations. Remember the intuition of primal dual method is nothing but applying Newton's method in solving nonlinear equations. It turns out that the convergence of Newton's method largely depends on the Jacobian of this matrix here, right? The Jacobian matrix. If it's a non-singular, according to some of the materials, if you are close to the root, then Newton's method have good convergence. But what does it mean to be close to the root? Usually it's not clear, right? But there are some extensions of Newton's method that guarantee good convergence. So to summarize, the most important thing for the convergence of Newton's method is whether this Jacobian matrix is singular or non-singular, right? So having this in mind, then whether this diagonal element in the Jacobian matrix is 0 or not, determine whether this matrix is singular or not, right? That's why you cannot have the complementary condition strictly hold, right? If that strictly hold, then you have some of this hx equals to 0. You have a singular Jacobian matrix. That's why we have the perturbed KKT condition. That's from what I understand now. Okay, so let's start a new lecture. We are going to talk about modeling of discrete and continuous decisions in lecture 11. So we will break down this into two parts. First part is on how do we formulate good nonlinear programming models, right? So that's the last thing we want to talk about for nonlinear programming. Then we will switch gears and talk about mixed integer linear programming and how do we formulate mixed integer linear programming models. So a couple of guidelines for modeling nonlinear programming problem. The motivation of doing this is that besides developing some robust methods, of course you want to have good scaling of the algorithm with some pre-solved technique and so forth. Having a good model also helps, right? Usually if you are just interested in the application, you would like to formulate a good model before you throw that to a solver. So the first guideline is it would be nice to specify the lower and upper bounds for all the variables. If you know good upper and lower bounds from your problem, it would be nice to specify that. This guideline is not as significant in convex problem. So in the latter half of this lecture, we will talk about non-convex optimization problem. In non-convex problem, specifying variable bounds will actually play a significant role in solving those problems. Yeah, so the reason is that this leads to more constrained feasible regions and provides you with a good starting point for the problems. And if possible, you would like to provide upper and lower bounds such that they are as tight as possible because that will shrink the feasible region of the problem and help you get a good solution. Okay, the second guideline is quite straightforward. That says whenever possible, you would like to linearize the problem, right? If you can formulate the problem as a linear problem, do not formulate as a nonlinear problem. Here's a simple example to demonstrate the idea. So if you have a constraint like this, saying like x1 over x2 to be less than or equal to 2, and x2 is non-negative, right? It's very simple. You can linearize this just by multiply x2 on both sides. Since it's greater than or equal to 0, then this is nothing but this linear inequality here, right? Again, if you have a convex nonlinear constraints, it's not as significant, but if you have something like this, which is non-convex, it's better to linearize it, right? In the second half of this class, we are going to show you some examples of how do you translate a non-convex constraint to a convex one. There are some applications you can do that. Okay. And the other thing is called scaling, right? This is to avoid numerical issues for the problem. As you can imagine, when you are doing interior point methods, in each iteration of the interior point method, you are essentially solving a linear system, right? You are essentially solving ax equals to b, and you solve for x, right? That means you need to take the inverse of the matrix and so forth. And if you have some numbers which are very different in their magnitude, usually those linear systems can be U-conditioned. For example, if you have x1 between 0 and 1, x2 is between 0 and 10,000, right? In this case, your matrix usually have a pretty large condition number. You don't want that to happen. So what you can do is just define a new variable that's called z. Z is x2 divided by 10,000. And you just, whenever you need to use variable x2, you use z2. That's it. Okay. This should be straightforward to understand. So the other trick for solving nonlinear programming problem is to warm start nonlinear programming problem. Supposedly you already know a good feasible solution for the NLP. It would be nice if you can, just give an initial starting point for the algorithm. As you remember, either the barrier algorithm or the interior point method, you are warm starting your algorithm from the previous iteration, right? Remember, you are gradually increasing this number t, and for each number t, you are solving a Newton system for the barrier method, right? For the primal dual method, we are also trying to increase t at each iteration, and at each iteration, you are warm starting from the previous one, right? So you can have a very good initial starting point, that helps a lot. But not all the interior point solvers are amenable to warm start. For example, we talk about two solvers. One is called IP-opt. It allows warm start, meaning that if you, for example, I will show you how to do that in PyOmo in the next slide, right? For example, if you give the values to all the variables as warm start values, so IP-opt will take your initial point. But Mosaic is another interior point solver. It doesn't take your initial point, right? It believes that, it doesn't really believe initial starting point actually helps interior point methods, right? These are some implementation details. So IP-opt have some tailored techniques to warm start interior point method. But Mosaic believes usually, even if you provide a good initial starting point, it doesn't help that much. Okay, those are some implementation details. But if you have a linear programming solver, let's say you are using a simplex method, either primal or dual simplex method, they do benefit a lot from warm start. The reason is that warm starting linear programming methods is much more straightforward than warm starting interior point method. Think about if you gave a basic feasible solution to a simplex method, right? Then it can just start from that basic feasible solution and then continue iterating over the simplex method, right? If the basic feasible solution you gave is very close to the optimal basic feasible solution, then the simplex method would converge pretty fast. But for interior point method, the property is not as strong, right? We know intuitively, if you warm start from a previous iteration, you have a fewer Newton's iteration, right? But it's not as straightforward as warm starting simplex methods. So here I have a comment here. Overall, the linear programming solvers are easier to warm start than NLP solvers. These have implications in solving integer constraint problem as well, because solving mixed integer linear programming problems are much faster than solving mixed integer nonlinear programming problem. One of the key reasons is that LP is easier to warm start, right? We will see that in a second when we talk about mixed integer linear programming problem. So if you would like to warm start the solver, here's how you do it in PyOmo. Okay, so you can let's suppose this is your model. The model only has two variables. Of course, your model will have way more variables than two variables. But here's the syntax to do that. You just set the value of the variables to the warm start values you want. For example, here the y naught is equal to 1, y1 is equal to 0. And then you can pick your favorite solver. Let's say we pick Cplex. You can use Groovy or IPOpt, all the solvers that are amenable to warm start. And you can do opt.solve model, and then you set warm start equals to true. Then the solver will take the warm start value you set. Okay. So here's everything I want to talk about for formulating nonlinear programming models. Any questions before we move to an entirely different topic? Okay. So there are not much math here. Hopefully this should be easy to understand. Okay. So in the next few lectures, we are going to talk about mixed integer linear programming. So what it is supposedly we have variables x. So all these x are continuous variable. In other words, x, let's assume x is in n1 dimension, right? And we also have a bunch of integer variables. So y is of dimension n2, but it can only take integer values, right? In other words, they are discrete. And all the constraints are still linear. You have the objective is linear is A transpose X plus B transpose Y. And the constraints are also linear. It's AX plus BY less than or equal to D, right? So the difference between mixed integer linear programming and linear programming is that we have a subset of variables that are integrality constraint, right? But the difficulty here is that this problem is NP hard to solve in general. Remember, we talked about computational complexity at the beginning of this class. All the convex problems are polynomially solvable, right? But this MILP problem are NP hard to solve in general. And it has wide applications in engineering, healthcare, logistics, machine learning, and so on. I would argue that in practical applications, most of the practical applications are formulated as MILP problems. So this can be seen as if you go to the the web page of each of the commercial solver, you can check how much they are charging you per year, right? You'll quickly find out most of the MILP solvers are the most expensive one. It's just because they have a wider applications. The difference between MILP problem compared with LP or nonlinear programming problem is that they do not scale as well as a linear programming problem, right? For linear programming problem, you can easily solve millions or even billions of variables, right? But for MILP problem, the way you formulate a model will have a big influence on how fast those models can be solved by the algorithm. So that's why we want to talk a little bit about modeling here. We didn't talk much about modeling in linear programming problem because even if you have a very poor model, because the solvers are so good, then it can solve the problem relatively fast. But for MILP problem, although a lot of efforts have been spent on improving the solver, you can observe that from the Mittelman benchmark, how fast the solver gets improved over the years. But still solving those problems are quite challenging, especially for practical problem. Let's say if you go to work for a company that solves MILP problems, usually having a solver alone is not enough. You have to be able to develop some tailored methods for your specific applications. Okay. And another reason why modeling is non-trivial is because we usually use a binary variable to represent logic, right? So in continuous case, usually you use variable to represent things like physics or some continuous quantities, but representing logic is a little bit more complicated than just use the continuous variables. So in this class, we will tell you how do you translate logic to integer constraints. Yeah, so let's first show a couple of examples to demonstrate the power of modeling using 0-1 variables. Again, most of the case when you talk about integer programming, we are talking about 0-1 variables because you use 0-1 variable to represent logic, right? And you may argue that you may want to use integer variable to represent a given quantity that's integer, right? For example, in the diet problem, you may argue that you want to use the integer variable to represent, let's say, the number of eggs you eat per day, right? But those applications are not the main application of integer programming. The reason is that if you want to represent an integer quantity which is pretty large, let's say from 1 to 100, right? You can eat from 0 to 100 eggs per day. So the reason those problems are not very relevant is because if you have problems with integer values, you can just solve the linear programming problem and do a very simple rounding, and the solution won't be very different, right? Think about if you have an integer variable from 1 to 100, maybe you solve the linear programming problem and you get a solution, let's say 69.3, right? Then you can just give it 69. The solution won't be significantly different. And the case where solving integer programming problem would be very different than solving linear programming problem is when you have some logic decisions, right? Because you cannot say, if I do this, I don't do that. You cannot say, if I do a fractional number of this thing, I won't do a fractional number of that decision, right? So that's why when we talk about integer programming, we are talking about logic decisions, okay? Yeah. So here, let's say we use some binary variables yj to represent the logic. If let's say if j is true, then we have yj equals to 1, and yj is 0 if j is false. So in order to represent at most one of yi and y1 and y2 is true, you may be tempted to write a constraint like this, right? So just let's write y1 times y2 equals to 0, right? If you multiply these two, they are 0, that means at least one of them are 0, right? Okay. So although this is the right way of writing a constraint, you are writing a constraint in a nonlinear way, right? So y1 times y2 is a nonlinear expression. Since we're talking about mixed integer linear programming, we would love to write everything in linear form. You will see quickly why you want a linear form instead of this nonlinear form. Okay. So I would argue that this nonlinear constraint is equivalent to this linear constraint, right? At most, one of y1 and y2 equals to 1. That means y1 plus y2 is less than or equal to 1. Right? These two things are equivalent. A nice thing is that this constraint here is MILP representable. Right? You can write it as a linear constraint. So why do we want to write it as a linear constraint? The main reason is that if you look at the continuous relaxation. So continuous relaxation means, let's say you remove the binary constraint, you just let the y variable to be a continuous value between 0 and 1, okay? So for the first problem, the continuous relaxation is y1, y2 equals to 0, and then y1 and y2 are both from 0 to 1, right? So in this case, if you look at the continuous relaxation, it will be these two black lines here, right? That's a continuous relaxation of y1, y2 equals to 0, and they are between 0 and 1. It is very clear that this is a non-convex region, right? So if you are talking about these two lines here, it is very clear it's a non-convex. You pick any 2 points and pick a line segment, they are not in the region. But if you are talking about the linear constraints, y1 plus y2 less than or equal to 1, and y1, y2 from 0 and 1, we are talking about a convex region, which is this shaded blue region here. Right? It is convex. So that's why you prefer the linear constraints. Yeah. So here's another application of a binary constraint, which we call big M constraints. You will see that quite often in the applications of mixed integer linear programming. So let's suppose we want to represent this logic here. If y equals to 1, then I want to enforce an equality constraint. Okay. And suppose hx equals to 0 is a simple nonlinear constraint representing the condition. Okay. And then we can represent this logic using this nonlinear equation here. Yes?
In the previous slide,
Yeah.
you again explained why is y1, y2 equal to 0 bound functions?
Yeah, so if you look at this y1, y2 equals to 0, and then their values are between 0 and 1, it's essentially this line segment here and this line segment here, right? And it's clearly the two-line segment is not a convex region, right? By definition of convexity, if you pick any 2 points in the set, their convex combination are in the set, right? If you just pick these 2 points here and connect them by a line segment, they are not in this two-line segment, right? Yeah. Other questions? Yeah, so let's continue about the big M constraints. Recall that what we want to express is if y1 equals to 1, then we have this constraint hold, right? And it's easy to see that this logic can be expressed as y times h of x equals to 0, right? Remember, y can only take values 0, 1, right? First, recognize that when y equals to 0, this equation trivially holds, right? If y equals to 0, then we just get 0 equals to 0, right? On the other hand, if y equals to 1, then we basically have, since y equals to 1, here this equation will be reduced to hx equals to 0, right? So that's a correct way of representing the logic, okay? Now the only caveat here is that if hx is linear, this equation destroys linearity, right? We do want to keep all the constraints linear. For example, if the hx is, if hx is a transpose x equals to, let's say a transpose x minus b equals to 0, this is hx. Then we will have something y times h of x will be y times a transpose x minus b equals to 0. Now you have a nonlinear term which is y times x, right? As we argued in the previous slide, we would prefer to keep the problem linear, right? Since you have a convex relaxation. So just a little bit boiler alert, which is whenever you solve a mixed integer programming problem, it relies on having a good convex relaxation, right? Then you can kind of use a convex relaxation to solve a non-convex problem. Yeah. Now the question is, how do we avoid this issue of having a nonlinear, yes?
Y is a constant here, right?
Yeah, so y is a binary variable. Y can be either 0 or 1. Yeah.
So how is y times x nonlinear? Then, like, if x is a vector, then the constant just multiplies to both.
Yeah, so that's a good question. Think about this. So in order to solve those problems, we haven't talked about the algorithm to solve this problem yet. Okay, we will talk about in the next lecture. But the algorithm to solve mixed integer problem all rely on continuous relaxations. Okay, so maybe you can develop other smarter ways of solving mixed integer programming problem that does not rely on continuous relaxation. Then perhaps this is a good formulation. But I would say up until now, all the good methods to solve mixed integer linear programming problem rely on continuous relaxations, right? So if you take the continuous relaxations of this problem, even though y is binary, its continuous relaxation is between 0 and 1, right? Just like the previous slides, we don't like a continuous relaxation that is non-convex. Okay, it's the same logic here. We do not want this continuous relaxation to be a non-convex region. Okay. Yeah, so to avoid this non-convexity here, we will introduce something called big M constraints. The way it works is the following. So you have Hx here, and then you have a parameter M. This parameter is a so-called big M parameter in mixed integer programming. On both sides of the equation, you have minus big M times 1 minus y and M times 1 minus y. So let's check what will happen in two scenarios. Supposedly, if y equals to 1, then if y equals 1, you can find that this side will be 0 and this part will be 0 when y equals to 1. Then this reduces to hx equals to 0, right? So on the two inequality is h between 0 and 0. That's why you have this equation hold. On the other hand, if you have y equals to 0, then this reduces to hx is between two big M parameters, right? So this also trivially hold because if you pick a sufficiently large big M parameter, then this is still a valid constraint, right? What does it mean to be sufficiently large? That means you pick the M value large enough such that this does not cut your optimal solution. Okay, and it is not trivial to pick those big M parameters. We will talk about some applications, and then you will get some intuition on how to pick those big M values. All right. The idea is, let's say you have a way to pick a sufficiently large one, but in practice, on the one hand, you want a sufficiently large big M. But you also want this value to be as small as possible such that you are not cutting off a big chunk of your solution space. Okay? Yeah. So the reason we want to pick a big M as small as possible is, first of all, there are numerical issues with a super large big M parameter. And the second thing is that the relaxation will be tighter if you have a smaller big M. We will come back to this point from time to time here. Okay, you can just remember, for now you can just remember you pick a sufficiently big M value, and on the other hand, you want it to be as small as possible. Okay, and then we will come back to this point in the future. Questions here? Yeah. So here's a few other ways of using the binary variables. In some of the applications, you may want to express something like, I want to select at least one of the objects in this set J, right? Then you can represent as the summation of yj to be greater than or equal to 1. And if you want to say, I want to select exactly one of the binary variables, then that will be the sum of yj exactly equals to 1. And if you want to say select not more than one of the variables, that will be the sum less than or equal to 1. Right? And this should be straightforward. In some instances, you may want to represent a if-then condition, right? So let's assume you want to express a condition. If we select k, then we are going to select j as well, right? So this is like an implication condition. Yk implies yj, right? So how do we express that? You can express this as a constraint yk minus yj less than or equal to 0. Why this is true? Because if you have yk equals to 1, then this constraint will force yj equals to 1 as well, right? Since yk is true, implies yj is also true. If you have yj greater than or equal to yk, then this condition holds. On the other hand, if you have yk equals to 0, then it does not imply anything, right? Yj can be either 0 and 1. And this constraint will just reduce to yj greater than or equal to 0, and that means it doesn't constrain yj at all. Okay. And if you want to express a condition if, that means if and only if, then you can use you can just use yk equals to yj, right? Yeah. So those simple instances should be straightforward. And another thing you may encounter in practical application is the so-called disjunction. So what disjunction means is the following. If you have two constraints, f1x less than or equal to 0 and f2x less than or equal to 0. If you want to express either this constraint holds or this constraint hold, then we can use this disjunction. Use this big M type of constraint to represent this disjunction. We will come back to this at the end of this lecture again. Okay. So here, if you observe this system of inequalities, we have two binary variables, y1 and y2. So y1 represent the first constraint have to hold. Y2 represent the second constraint has to hold, right? Then if you have y1 plus y2 equals to 1, that means only one of them can hold, right? Then if you have y1 equals to 1, then y2 must be equal to 0. Then these two inequalities will be reduced to f1 of x less than or equal to 0 and f2x less than or equal to a big M value. That means the first constraint has to hold, then the second constraint will hold trivially. You just pick a big M value that is as large as possible for it to hold, right? Similarly, by symmetry, if you have y1 equal to 0, y2 equals to 1, then we have the second constraint hold, and second constraint. Oh yes, this should be f1 less than or equal to big M. Okay. Yeah. Questions here? Yes.
Do you have multiple big M values for like different constraints, or is it just one number?
Yeah, that's a very good point. You should for each of the constraints, you should pick the big M as small as possible. Okay. Right? That will help your problem. We will come back to this point later. Okay. Yeah. Yeah. So the next application we are going to talk about is how to represent a discontinuous function, right? Remember, when we talk about convex optimization or linear programming and so forth, all the functions are continuous, right? That's why you can take gradient and so forth. But in some of the scenarios, a function can be discontinuous. And practical application is a fixed charge model describing the cost of equipment, right? So let's say if you are buying equipment, right? Let's say I'm a chemical engineer, so I will use a heat exchanger, okay? So if you are buying a heat exchanger, there will be a fixed cost and a variable cost associated with a heat exchanger. The fixed cost meaning that as long as you are buying a heat exchanger, that's a cost you have to pay, right? No matter how large the heat exchanger is. And the variable cost, the beta, is something proportional to the size of the heat exchanger, okay? And the size of the heat exchanger has to be between L and U. That specifies, the size limitation of the manufacturer, right? They cannot manufacture a super tiny heat exchanger sit on your table, right? So that's why you have a L here, okay? If you look at the domain of the function, it is discontinuous, right? So if you don't buy a heat exchanger, of course, the cost is 0 here. But if you ever want to buy a heat exchanger, then the size is between L and U. So let's say this is L, this is U, right? And between 0 and L, this problem is undefined, right? You cannot buy a heat exchanger between 0 and L, okay? Yeah, so how do we represent this using a MILP representable function? So the way you can represent that is follows. You just set C equals to alpha y plus beta x. So here y is a binary variable that decides whether you are buying a heat exchanger or not. Right? So if you are buying y equals to 1, then you have to pay a fixed cost of alpha. Okay? And once you decide you are buying a heat exchanger, then the size of x has to be between L and U. Right? If you are not buying a heat exchanger, then y equals to 0. This constraint false x equals to 0. Yes?
Isn't C has to be like alpha plus beta x multiplied by y, or is it just?
Say that again?
Isn't C has to be like alpha y plus beta x y, or is it just like alpha only y is multiplied by alpha?
Oh yeah, that's a good point, because you are saying like, do you need to multiply x by y here? That's what. Yeah. So that's a good point. The main reason is that you don't want to have nonlinearity here, right? If you have x multiplied by y, then you have again you have a non-convex relaxation, right? So this non-convexity is avoided by. So if you think about this constraint, it is something like a big M type of constraint, right? The big M value is this U and L here, right? If y is equal to 0, then x will be forced to 0, right? So that's a trick here. Again, if you have y equals to 0, according to this constraint here, x will be forced to 0 and c equals to 0. If y equals to 1, then it forces x to be L and U, and c is equal to alpha plus beta x, right? And then what happens if you happen to have a lower bound equal to 0, right? This can be problematic because when x equal to 0, then y can be either 0 or 1, right? If you have this L equals to 0. But usually y will take y equals to 0, since usually in an optimization problem you are minimizing the cost, right? Since you are minimizing the cost, when you are not getting the heat exchanger, y will always take value 0. Okay. Any questions before we move to the next subtopic? Yeah. So those small applications should be pretty intuitive. Now we are going to show you a very systematic way of modeling logic into mixed integer linear programming. I'm sure you have heard about propositional logic in your previous class, maybe even in your high school or freshman year, you have heard about those logic. Just to define the notation here, this means the OR operator, meaning at least one of them is true, and this means AND operator, this means not, this means implication, this means exclusive. Exclusive OR means either A is true or B is true. They cannot be true at the same time. Okay, and this means equivalence. Right, equivalence is just the two logic are similar. A is true. A and B can be true at the same time or false at the same time. So if this is not intuitive, you must have heard about this thing called the truth table, right? So if you look at the OR operator, in the first two columns, we are outlining the values of A and B. The third column is the values of A or B. As you can see, when you are doing this OR operator, if one of A or B is true, then A or B will be true, right? A or B is only false when you have both A and B being false. Similarly, the NOT operator is very straightforward, right? When A is true, then the NOT A is false. When A is false, NOT A is true. So maybe let's talk a little bit about, let's talk a little bit about implication. You can read all the other. This should be very straightforward, right? So when you talk about the implication operator, that says when A is true, then B has to be true, right? So that's why when you have A is true, B is true, then A implies B is true, right? But if you have A is true, B is false, then A implies B is false, right? Because when this implication operator means whenever A is true, B has to be true, right? So if you have A equals to true, B equals to false, then A implies B will be false, right? But on the other hand, if you have A is false, then B can be either true or false, right? It doesn't matter here. So that's why whenever you have A is equals to false, A implies B will all equals to true, okay? And all the others should be pretty straightforward, like and equivalence and exclusive OR. We can come back to it later on. Yeah. Any questions? Okay. Yes.
Can you like do the opposite with the implication? I guess like if A is false, then B must be false as well. Do you have to like combine operators?
Oh, so you want to express that type of logic?
Yeah.
Yeah. We will tell you how to express
Okay.
this type of logic, right? Okay. So now let's talk a little bit about the so-called calculus of logic operators, right? So we will talk about this six. Let's call it the six basic logic operators. Yes.
So for the implication, are A and B independent? of
I-
each other?
Yeah. Let's assume all those are independent. They can take any arbitrary values.
So
right?
if B is false and A is true,
Yeah.
then why cannot A imply B, like if they're independent?
Why say that again? When
Like if A and B are independent and
Yeah.
B is false and A is true, there's no connection between them, but then why cannot A like imply B to be true?
yeah. So this is more like when you have so you can express that, but this truth table is just saying when this let's argue a little bit about what we are trying to do with this truth table, maybe. Okay, so the truth table meaning that if I want to express this logic, then I'm trying to check what are the A and B values that make this implication true. Okay, so that's my motivation of having the truth table. Okay, it's more like if I want to express A implies B, then what conditions A and B has to satisfy. That's okay. And that's the main thing we want to cover. Okay, so let's go to the next point, which is the calculus of logic operators. So now you have already seen the six basic logic operators, right? Now the question is, if we are going to combine those logic operators in a very arbitrary way, then how do we do the calculus, right? It's also, analogy can be made. You can define things like plus, minus, division, multiply, right? You have defined those, let's say, arithmetic operators. Then there are some rules those operators have to be following, right? So that's what we are going to talk about here. And the first thing we are going to talk about is the De theorem, right? So that says if you put a not operator outside a parenthesis, then this is equivalent to not A and not B. Right? So in other words, you are changing this all to and if you apply a negation from the outside. Okay. So how do we prove that? A simple proof can be shown using the truth table. Okay, so let's just show it using the truth table why the De theorem is true. So let's say the first column is A, second is B, then we have A or B, and the negation of A or B. Okay, And now the values of A and B can be, let's say, true, 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 false. Right? So that's what the values of A and B can take. Then A or B is true whenever A or B is true, right? So this will be true. Oh yeah, that's a mistake here. False, false. Okay, so that's a truth table for A or B. And the negation of A or B is just you take the negation of this column, right? That will be nothing but false, 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 true, right? Okay. And now if you think about the right-hand side is the negation of A and the negation of B. Take the and, right? So first let's do not A and not B first, right? And this would be false, false, true, true, and then this is false, true. Right? You just take the for this column, you just take the negation of this column and so forth. And now let's do not A and not B, right? So not A and not B is only true if these two columns are both true, right? So the only true row is the last one. All the others are false, right? So if you check this this column and this column here, they are equal to each other, right? Yeah. So you can prove all those calculus using the truth table, right? Again, the motivation of doing the truth table is that you want to prove that these two logic propositions are equivalent when you have A and B taking any arbitrary values. Okay. And similarly, the other side of De Morgan's theorem is that if you have and at the center, if you take the not, the and will be changed to the or. Okay. And there are other theorems you can prove using the truth table. One is the distribution of or. Analogy can be made is that if you want to distribute the multiplication in a class, right? So if you do let's say A plus B times C, this is nothing but AC plus BC, right? That's a distribution rule in arithmetic operations. But in logic operation, it actually have the same thing, right? If you want to distribute an or into an AND operator, you will just do A or B and B or C, right? Again, the proof is from the truth table. And similarly, if you want to distribute the AND to an OR operator, that will be A or C or B and C. Right? There is some symmetry here. And the implication is equivalent to negation of A or B. Okay, you can also prove using the truth table, or you can argue it from a logic point of view. So if A is true, then not A must be false, right? Then because you have all operators here, when A is true, this guy is already false, then B must be true, right? That's an implication. Okay. Any questions for this part? Okay. Yeah. So if you want to prove that, then you can just use the truth table, or you can just keep this as a cheat sheet when you solve logic problem, right? It's all right. Yeah, so how do we express those logic propositions as constraints? right? So at the end of the day, we want to represent those logic as an optimization problem. Then we can associate each of those logic using a binary variable, right? So the true and false will be associated with a binary variable that takes values 0 and 1, right? So you want to say not pj, you can express this as 1 minus yj, right? Yj is a binary variable here, okay? And if you want to say or pi or pj, that means at least one of this binary variable is equal to 1. Then you can represent this as yi plus ij greater than or equal to 1. And if you want to express and pi and pj, then yi and yj both have to be equal to 1. And the implication can be written equivalently as not pi or pj, right? Then it can be represented as, right? You can use by combining the not and or, you can express this not pi or pj, right? Then that would be 1 minus yi plus yj greater than or equal to 1, and you can simplify this to yi greater than or equal to yj. Yes?
Y less equal to yj?
Oh, yeah, you are right. Thank you. Yes. Okay. Yeah. And for exclusive OR, then it is equivalent to yi plus yj equals to 1, and equivalence would mean yi equals to yj, right? Okay, that's just a simple way of expressing all the we have 6 logic expressions in terms of constraints. Okay. Hope it is clear here. Now the question is, how do we represent a more general logic proposition using constraints, right? We've already done the 6 basic operators, but in practice, you may want to express more complicated logic. Like the 2 examples I gave here, right? Maybe you want to say P1 or P1 and P2 implies P3 and P4, right? Or you want to say P sub F implies, so let's remove this part. It doesn't make sense here. So it implies PD and not PM, right? If you look at this, and maybe if you guys are very smart, maybe you look at this for some time, then you are able to express this as constraints, right? But you have to think about this on the fly. It is not as straightforward as the simple operators. Yeah. So in the next few slides, we are going to cover a very systematic way such that you can convert any logic propositions, no matter how complicated they are, into integer constraints. Okay, that's what we are going to do next. Yeah. So before we talk about arbitrary logic constraints, we want to cover a very important property in logic. It is called a functional completeness. Okay. So what does it mean to be functionally complete? So if you think about all those logic propositions, any of their combinations, functional complete says you only need 2 logic operators, the and not, to express any truth table you wish. Right? So it is a very powerful theorem. Right? It says although you can have different logic operators, we have introduced 6 different logic operators. But the functional complete theorem is saying that you don't need all the 6 logic operators. As a matter of fact, you can use 2 logic operators to construct any logic proposition, or in other words, any truth table if you wish. Okay. So why this is true, you can see that in a second. So here we are just showing a very, let's say this is a partial proof of this theorem. Since we are only using 2 logic operators, and then maybe you wonder, how do we replace all the other 4 logic operators we have introduced using the and not, right? So here's a very simple proof of that. So if you want to express the all operators, you can replace it with a not and operator just by applying this De Morgan's rule. Okay. And if you want to express a exclusive OR operator, note that exclusive OR means either A is true, B is false, or A is false, B is true. That it means to be exclusive OR, right? So exclusive OR is equivalent to this, and you can show further that you can replace the OR operation with the and not operator. Okay, and similarly, you can show that implication and equivalence can also be replaced by not and operator. Okay. So what does that imply? That implies if you can express any logic that use and not operator, then you are fine, right? You can express any possible logic using and not. Okay. But we are not going to just use and not, because in practice, maybe it is more intuitive to use more logic operator, right? If I only give you 2 logic operators, although you can do something more complicated, this is quite long to express it just using and not, right? So we are going to show you a way where we assume one may write logic propositions using not just and not, but we allow people to use or and implication. Right? Of course, if you are fine with only and not, if I give you 2 more, or and implication, of course you are more than fine. Right? You can express pretty much all the logic expression using these 4 logic expressions. Right? And next, we are going to show you a way, right? If you have a proposition logic using these 4 operators, we can always convert it into integer constraints, right? Okay, so this is a little bit convoluted. Let me go back and say that again. Okay, so the motivation of this section is saying that we want to convert any arbitrary logic expression or logic propositions into integer constraints, right? Then how we are going to do that? First of all, we show that if you have these 4 logic operators, it can represent any arbitrary logic expression. Why this 4 is enough? Because this 2 is already enough, right? Of course, this 4 is enough to represent all the logic propositions. Then in the next step, we are going to show you, given any proposition logic using these 4 operators, we can always convert it into integer constraints. Okay, so that's what we are going to do next. Okay, so in order to do that, we are going to introduce a concept called conjunctive normal form. So the reason we want to introduce conjunctive normal form is because conjunctive normal form can be easily represented as integer constraints, right? So that's number 1. Then the second thing we are going to show is any logic expressions can be converted to conjunctive normal form. Okay, so we'll first show that conjunctive normal form can be converted to integer constraints. Then we show all the logic expressions can be converted to conjunctive normal form. Then with these 2 building blocks, you can show that all the logic expression can be converted to integer constraints. Okay, yeah. So what is a conjunctive normal form? It means you have a logic expression where the conjunction is you have a conjunction of disjunction. In other words, this logic expression is in this form. You have a bunch of AND operators in the outer loop, and for each of these logic operators in the conjunction, you have an OR operator. Okay, so let me give a simple example of what is CNF. So if you have P1 and, should have this. If you have P1 or P2 and negation of P3 or P4, it is a conjunctive normal form. Why it is that way? Because the AND operators is outside the parenthesis, and within the parenthesis you only have the OR operator. Okay. Yeah, and this I means the difference between II and PI is each of these literal can be either a proposition PI or its negation. For example, here I have the negation of P3 here, okay? Yeah, so that's what it means to be a conjunctive normal form. You have the AND operator outside the parenthesis, and within the parenthesis, you can have an arbitrary number of OR operator, right? Okay. So why the CNF can be easily converted to integer constraint, right? Yeah, so here's an example very similar to the one I just wrote. If you consider a CNF of this form, right? So this is the first parenthesis, this is the second. And since the AND operator is outside the parenthesis, right? Since you have AND, right? So whenever you have an AND operator, that means this thing has to be true, this thing has to be true in order for the whole CNF to be true, right? So because you have the AND operator outside the parenthesis, it is equivalent to say each of the logic expressions in each of the parentheses are true, right? Since you have the AND operator outside of them, okay? So here we have two of those, right? Then this logic expression is saying that this OR operator is true, this OR operator is also true, right? And the first one is equivalent to y1 plus 1 minus y2 greater than or equal to 0, right? Okay. And you can observe that writing this, let's call it disjunction as an integer constraint is also very simple, right? You just sum them up, at least one of them has to be true, right? You just sum them up and let them to be greater than or equal to 0, okay? So that's how you can convert the CNF into two linear inequality constraints, okay? Any questions for this small example? Yeah. Okay, so in general, how do you translate a CNF into constraints? Okay. Recall that the CNF is this form. You have AND outside and OR within the parenthesis, right? Yeah. And each of these OR operator in the parenthesis has to hold, and you can model this OR operator as the summation over yi prime has to be greater than or equal to 1. And yi prime is equal to yi if you don't have a not operator in front of them, right? If you have a not operator in front of them, then the yi prime will be equal to 1 minus yi, right? Oh. That's what I mean here. So if you have a, let's say, P1 or P2 or negation of P3 to be the OR operator, then that says y1 plus y2 plus, since you have a not in front of P3, then that means you should turn this to 1 minus y3 greater than equal to 1. Right? That's what it means. All right. Any questions for this part? Okay. Yeah, so we've already covered how do you translate a CNF into constraint. The next thing we should cover is how do you translate any logic proposition into a CNF, right? Because we know once you translate the logic proposition into a CNF, then it's easy, right? Okay, so now we have a recipe of translating any logic proposition into a CNF. Let's suppose the logic proposition can have and or not implication. Since we already showed that if you have these 4 operators, you can express any logic, right? So let's say if you have those 4 operators, how far are we from a CNF, right? First thing you want to remove is implication, right? Because in a in a CNF, it doesn't have any implication, right? So you can always remove implications using this fact, right? The implication is equivalent to not A or B, right? So using this fact, you can remove all the implications, right? If you have some nasty implication, you can apply this fact recursively, okay? And the second thing is that in the CNF, the negation are always associated with those, let's call it maybe logic variable, right? So we always have, we don't have negations outside the parentheses, right? The negations are associated with those logic variables. So you can use De Morgan's theorem to move the negation inwards, right? Just apply this recursively, then we can get rid of the parentheses. Now the other thing we have to take care about is we have to put the and outside the parenthesis, right? So if you have something like this form here, where the and is within the parenthesis, right? Then you can apply this distribution rule to put the and outside, okay? So it has been proved that if you apply these 3 steps recursively, then you will always get a CNF, okay? It might, okay, so now let's show a quick example of how do we convert a given problem into CNF. Yeah, so let's write down the context of this problem. Yeah, so I'm going to use a chemical engineering example. Even if you are not a chemical engineer, this should also be very straightforward, right? So we consider a process synthesis problem where the statement says if we select flash, then select distillation and not membrane. Okay, so the logic should be clear, right? So the decisions you want to make is that whether you select a flash or not, and whether you select distillation or membrane or not. But they have to satisfy this logic constraint that says whenever you select flash, then you have to select distillation and not membrane. Right? You can think about this as a logic constraint in your optimization problem. Right? So let's represent, since we have 3 decisions to make, right? Then we use, let's say, maybe we use a variable PF to represent whether we select flash or not, and PD to represent whether we select distillation or not, and then this is P sub M. Right? So how do we represent a logic proposition here? Okay, I would say that the logic proposition we talk about is PF implies PD and not PM, right? Okay, in other words, when flash is selected, that implies we have to select distillation and not selecting membrane, right? That's a logic you want to express. Now we want to translate this into a conjunctive normal form. First of all, we have to remove the implication, right? So the implication is equivalent to negation of PF or this term, right? Okay, so that's just the application of the implication part. Now we are still not in a CNF form, right? Because the and is within the parenthesis. We want to move the and outside. Then you can apply the distribution of or over and. That will be PF or PD. And then you have not PF or not PM, right? Now we are done, right? This is a CNF form already. The and is outside the parenthesis, and within the parenthesis you only have or. Okay. Now we can translate this into constraint, right? So since you have the and here, you just enforce the two and respectively, right? The first constraint will be 1 minus YF plus YD greater than or equal to 1. Then you have 1 minus YF plus 1 minus YM greater than or equal to 1, right? Okay. So if you enforce these two constraints in your optimization problem, then the logic in your optimization problem will satisfy these logic constraints, right? And as you can imagine, the way you are going to use those logic are related to designing some chemical plant, right? In other areas, like maybe, I don't know, maybe mechanical design, you may also have similar problem, right? You want to express some logic constraint within an optimization problem. Okay, so I will need some time to move to the next topic. Maybe let's just stop here, then we can continue this lecture on Thursday.